We have seen how to compute the eigenvectors and eigenvalues of a matrix. Let me show you a few shortcuts, a few tricks for a 2x2 matrix, and then we will generalize these tricks to a general larger matrix. So sometimes this collection of eigenvalues and eigenvectors is in one expression denoted by eigensystem. Consider a general 2x2 matrix with entries A, B, C, D. The characteristic equation is A minus lambda E is 0. So let me first determinant of that. So let me first prepare this. We take the matrix A and we subtract lambda from the entries on the main diagonal. A minus lambda, B, C are unchanged, and D minus lambda, and determinant of that. And if we compute this determinant, we have A minus lambda times D minus lambda minus BC. So we have AD minus A lambda minus B lambda minus BC plus lambda squared, sorry. It should be somewhere here. So this is lambda squared, and from these two terms we can factor out lambda, and we have minus bracket A plus D times lambda plus AD minus BC. And we want this to be equal to 0. So this is a quadratic equation. Do you recognize this expression, AD minus BC? This is the determinant of the matrix. And this expression, A plus D, is also an important expression, so important it has its name. This is called trace of the matrix. Denoted by TR. And this is the sum of the entries on the principal diagonal. For a 2x2 matrix, this is A plus D, or A11 plus A22. In general, for a larger matrix, it would be sum of I running from 1 to n. That means that the number of the row is equal to the number of the column. These are the entries on the principal diagonal. And we sum, we add all of them. So this is the trace. So here we have the trace of the matrix. So the characteristic equation can be written for a 2x2 matrix, can be written as lambda squared minus trace of the matrix times lambda plus determinant of the matrix is equal to 0. It is so nice for a 2x2 matrix. For larger matrices, there will be more terms. But if we consider the quadratic equation in the form lambda minus lambda 1 times lambda minus lambda 2, well, lambda 1 and lambda 2 are the roots, and if we expand this multiplication, we have lambda squared minus lambda 1 plus lambda 2 lambda plus lambda 1 times lambda 2. And if you compare these two forms of the quadratic equation, then we see that the determinant of the matrix is equal to lambda 1 plus lambda 2 times the product of the eigenvalues. It is so easy to show for a 2x2 matrix But this is true for any matrix, that the product of eigenvalues is equal to the determinant of the matrix. And similarly, as we use capital Greek sigma for sum, then we can use a capital Greek pi for a product. So the expression lambda 1 times lambda 2 up to times lambda n can be written as product of lambda I running from 1 to n. And if we multiply all the eigenvalues, then the product is equal to the determinant of the matrix. So this is an important result. Do you remember when we discussed the equivalent statements about the matrix concerning the determinant? The very last statement was the determinant is different from 0. This is equivalent to the statement that no eigenvalue is equal to 0. And this is not 0 if no eigenvalue is equal to 0. And then when we compare the coefficient at lambda, we see that the sum of the eigenvalues is equal to the trace of the matrix. And once again, it is so easy to show for a 2 by 2 matrix, but it is valid even for a large matrices. So the sum lambda 1 plus lambda 2 plus up to plus lambda n, which can be written as sum of lambda I running from 1 to n, which is the trace of the matrix. And this is again true for even large matrices. So this helps us to build the characteristic equation for a 2 by 2 matrix very quickly. If we go back to the matrix from the previous case, which was 1, 1, 2, 0, then we evaluate the trace, which is sum of the entries from the main diagonal. We compute the determinant, which is this times this minus this times this, and we can immediately write the characteristic equation. Lambda square minus trace times lambda plus the determinant. And we can check whether it was the same before. Lambda square minus lambda minus 2. Yes, it was, exactly. So this is a very quick way how to write down the characteristic equation for a 2 by 2 matrix. And one more abbreviation, one more trick, one more useful knowledge. When we solve this system, when we find the eigenvalues and want to find the eigenvectors, then this matrix A minus lambda E is from the A when we subtract lambda from the entries on the main diagonal. So when lambda 1 is 2, then we subtract 2 from 1, which gives minus 1. We copy 1 and 2, and we subtract 2 from 0, which is minus 2. And now we want to find a vector that gives 0. But this 0 means that the scalar product of this row and this vector is 0. Scalar product is 0 if the two vectors are orthogonal, if they are perpendicular. And it is easy to find a vector that is perpendicular to a given vector in a plane. We just swap the two coordinates and we multiply one of them by -1. So we take these two numbers, we multiply one of them by -1 and we swap them. So immediately we see that 1, is a good eigenvector. And similarly, for number 2, which was -1, the matrix A minus lambda E is generated from the matrix A when we subtract the eigenvalue from the entries on the diagonal. So we subtract -1, that means we add 1. So we have 1 plus 1 is 2. We copy 1, 2, and 0 plus 1 is 1. And once again, we want to find a vector which, well, yeah, then this is no more equal when we multiply by the vector. And once again, we want to find a vector that is perpendicular to the vector 1, 2. So we swap the two values from 1, 2 to from 2, 1 to 1, 2, and please multiply one of them by -1. So the second eigenvector would be 1 minus 2. 1 minus 2, yes, that's right. So these are some short tricks to find the eigenvalues and eigenvectors for a 2 by 2 matrix.